We're very happy to have Guido D'Amico from Stanford to talk to us about neutrino flavor and quark collapse supernovae.
Yeah, thank you for inviting me. Thank you for being here. So, as I was briefly mentioning to you at lunch, this is, I think, the first paper I will write on supernovae, and probably there will be another one, maybe other two, but on slightly different topics. Because I discovered that actually this is a real physics problem, in the sense that there is something that people really don't fully understand. And so we try to make progress in understanding, in this case, is the explosion mechanism. The progress that we make is not like a new theory, because there are already several ones, but we compute precisely the observable as actually measured by an experiment, and here in particular there will be JUNO. Calculations are done for this JUNO, which is an experiment being built in a mine in China, I think. You know anything about it? I think it's close to Shanghai, but yeah, I'm not entirely sure about the geography. But anyway, it's been built and will turn on next year, hopefully. And then we just need to wait for a supernovae to explode in our galaxy, maybe within my lifetime. Okay, so that's the outline. So I will talk about what we know about supernovae explosion and what we theorize as the mechanism, and in particular I will discuss this delayed neutrino mechanism, which is the one that most of the community thinks is the right mechanism, versus this one, which was actually the first one proposed in the 50s and then revived very, very recently, this collapse-induced thermonuclear explosion. And then I will explain the timescales and neutrino emission at the source, and then discuss the observable at Earth, and in particular there is a smoking gun, which is a statistics that we construct, but we also discuss a likelihood analysis, and I will tell you later. So just for those of you who don't know about supernovae, and please tell me if I'm boring you with this review, but I hope not, because at least it helped me to write these things like in terms that I understand, and not and not in astrophysical terms that sometimes are confusing. So basically, we all know that massive stars, and by massive I mean at least 10 solar masses, they have a short life, of order 1 to 10 mega years, and they die young, and they die spectacularly. They release in an explosion like order 10 to the 51 ergs within seconds. So the death of the star starts by a catastrophic collapse of inner core, because things don't provide any more pressure support, because there are no nuclear reaction possible. And so the real problem is, how does this catastrophic collapse of inner core transform into an explosion? And in general, are the two things related? So this is a zero-order history, just the facts that we know. So any star sets into quasi-equilibrium states. So the life of a star is a succession of quasi-equilibrium states, that happen by burning heavier and heavier elements that provide the pressure support against the gravitational pull until they are on peak. So when you produce iron, nickel, whatever, then there is no more energetics available to burn a higher element. Then, after that, what does the star do? Well, the star just implodes. But at some point there will be the degenerate electron pressure that supports the star. The Fermi pressure of electrons, it sets in, and the star keeps collapsing and accreting the core until this core has a Chandrasekhar mass order 1.5 solar masses. At this point, not even like the electron pressure support is enough. And so gravitational collapse sets in, and there is an inner part of the core which collapses homologously, like within the sound horizon. And the outer part is just in free fall, and it arrives later, after the collapse. Electron capture at some point becomes favorable. So I get a proto-neutron star, basically nuclear density matter. At this point, the equation state gets immediately much stiffer, so you have something relatively soft, and then at some point things get harder. You get like a nucleus, like a big nucleus basically. And then there is a pressure response.
Can we go back
Yes.
one step? I think I kind of, sorry, I think I followed that up to the third point, but
Yes.
but if the inner part is just gravitationally collapsing.
Yes.
So electron capture is becoming favorable for the stuff that's falling down.
No. For the inner part, because I mean you get the temperature and density so high that at this point electron get captured. So you have inverse Billet decays.
So it's still on its way to try
Yes,
to be a black
yes,
hole. It's
yes.
not there yet.
Yes, yeah. And it's the inner core that starts doing this, and this is very fast. But then, so you have to imagine all this core starts, and then at some point, of course, there will be a discontinuity because the sound, the information can only travel so fast. And so it's this center inner one that stiffens when the density becomes nuclear, basically. Okay. Then you get a pressure discontinuity, right? So you have something that collapses, and then at some point it stops and hardens. And so so the matter which comes in now finds something hard. So this is what is called an accretion shock, which then bounces back. So so this is like the simplest mechanism that you could think. Even before talking about neutrinos or anything else. This is like the hydrodynamical mechanism that people actually proposed like in the 60s. And then they immediately realized the following, that this shock that bounces back, it just cannot explode. And the reason is that it loses a lot of kinetic energy by neutrino emission and nuclei dissociation when it goes towards the matter that falls onto it. And so it quickly stalls and would slowly fall back into the core. So you need something to provide you a trigger for the explosion. So I have figures, which is much better. So this is the initial phase of collapse. Okay, so at this point, so this is the radius of the iron core, okay? 3,000 kilometers, so it's still pretty big. And you get the neutrino burst from the deleptonization. Okay, so this is when this is the electron capture part. So then you get something that some nucleus which is much smaller now at 100 kilometers, which is composed of very heavy nuclei and almost nuclear density, 10 to the 12 gram per centimeter cube. And here is where neutrinos in particular get trapped. So the star is opaque to neutrinos, and then at some point you get 10 times at 10 kilometers, order 10 kilometers, you get nuclear matter. Okay, so this is in 0.11 seconds, you get this hard core, and as you see now the velocity inverts. When things go in, they immediately bounce back. And so this is like the shock formation, and this is the shock propagation. There will be this matter that goes far away, and of course there is still matter outside that doesn't know what's happening at that moment, that still falls in. So this is in figures what's going on. So like here maybe you can see, so this is like nuclear matter, whatever that we don't know. This is like the protoneutron star. We still don't really know the composition. So these are nuclei, and these are free neutrons and protons because it becomes energetically favorable to dissociate the nuclei. But this process in particular, together with the neutrino emission, makes the shock lose a lot of kinetic energy. And in fact, there is this shock stagnation. So at some point, the shock just stalls. But here, in particular, these figures explain the neutrino heating. So the idea is that here, unfortunately, is too dark. But basically, there is this layer that effectively cools by neutrinos, and then there is this external layer where the shock is stalled that actually gets absorbs neutrinos, and the kinetic energy of neutrinos that come from the core is supposed to revive the shock and push it away, and that's the explosion. And then after that you will get neutrino cooling of the protoneutron star, and neutrino driven wing for the next 10 seconds. Notice that at some point after the neutrino, after the shock stalls, after the shock is revived, you get the neutrinos, and then the neutrinos of all flavors. So this is an important part, because you get nuclear matter that basically produces neutrinos thermally. Okay, are there questions about this, about the physics of this? Okay, good. Okay, so this is the first mechanism, which is the delayed neutrino mechanism. So the possible physics for the explosion is the revival of the shock. And energetics basically can work, because you say, oh, but neutrinos, how come that they can revive the shock? Well, So, I mean, neutrinos are actually the most, the largest component in energy of the star, and we are talking about 10 to the 53 erg that's emitted in neutrinos, and the explosion of the star is only 10 to the 51 erg, so you only need the 1% of the energy being transferred to the shock. So we are talking about these numbers. Neutrinos, which cool the core, is absorbed in outer layers and revives the shock. However, it doesn't work in one-dimensional simulation. So if you try to do a simulation with all the correct neutrino physics and neutrino transport and so on, things which can become arbitrarily refined, in spherical symmetry, you will never make the star explode in the standard model. I mean, with the nuclear physics parameter that we have in our world. So there is still debate whether a self-consistent explosion arises in 2 and 3D. So most often 2D simulation, well, all 2D simulation basically, they introduce some numerical trigger to explode. So, and there is a huge debate in the literature. Some 3D simulation explode, but it's not clear whether it's purely by neutrinos. Probably there are other effects like magnetic fields or just convective convective layers that make the shock revive. So, but anyway, the defining feature of this mechanism, and now I think of this as representing a whole class of mechanism. So the defining feature is converting the inner core gravitational binding energy into an explosion. So it's converting 1% of the gravitational binding energy in the kinetic energy of the explosion. So this this can describe other kinds of mechanisms that you may think in the future. Okay, something that comes from the gravitational binding energy of the inner core. Now, another class of mechanism, and in particular, I talk about this collapse-induced thermonuclear explosion, but you may think of other crazy stuff, like, for instance, dark matter-induced explosion or whatever. So, what if the explosion is not related to the gravitational, to the inner core, but it just happens in the outer layers, okay? So this is this site mechanism that for which the infall is stopped 10,000 kilometers from the center by an angular momentum barrier. So we are talking about like very different numbers here, and whenever you get this barrier, which is now not like a pressure barrier, but it's an angular momentum barrier, the shock ignites a thermonuclear explosion in a helium-oxygen shell, and this is what we see. So, and the defining feature of all this is that the collapse is not related to inner core physics. Okay? Good. So, and now that's where we start analyzing the differences. So, what are the differences that we actually can see? So, one is a difference of time scales. So in the neutrino mechanism, the accretion shock must be revived within fractions of a second, because otherwise it just goes too much back in. And in this site, the supernova instead explodes after seconds, because the time scales of the outer layers are much longer. So we are talking about fraction of a second versus seconds, like order 10. And then the neutrino emission. Because in the neutrino mechanism, at some point, you immediately strip off the whole star, and you get a naked proto-neutron star, which gets all flavor on neutrino equally, basically by neutrino Graham-Stralsund. In sight, instead, I have normal matter. I have a lot of, all these outer layers are there. And so, since these things are dissociating nuclei, what you get is a lot of electron antineutrinos at the source. So these are the two differences. Question?
How do people abandon site, then how it's gathered?
That's a very interesting story. So, so site was proposed in this very famous paper B2FH in '59. So it's the paper that calculated all the nuclear reactions of the star. And then in an appendix, they write this as a mechanism. Then in the 60s, people started simulating. And then things didn't really work out numerically. And so it was just abandoned. And in the 70s, actually, people started thinking about this delayed neutrino mechanism. And you know, people like Bethe was working on it. And so I guess that this sounded right, and you know, probably sociologically it was also, you know, these people were influential. But basically, yeah, the site was abandoned because of some simulations in the 60s that didn't really work out, and then this other mechanism came in. And then, like, this mechanism has been around for like 40 years, and also the simulations don't really work. So at some point it's sociology, I guess. And the reason why I'm talking about it, because now actually there have been simulations that show that this mechanism is possible. Like, you have to have a star which is rotating, and then you can get this. Now the rotation might be pretty fast in the mechanism, in the papers that have been written. So the ratio of centrifugal to gravitational force is about order 0.5. So it must rotate a lot. But you know, in principle, it is possible and self-consistently explode. You do expect anyway start to rotate. So yeah. So these are the flavor profiles that you get. So notice the time scale after the bounce. So after, let's say, 0.2 seconds after the bounce, here is the ratio of the neutrino, electron antineutrino, to the heavy neutrinos. So if you have an explosion here, you will just get the cooling, and so this is close to 1. And instead, if you have an extended accretion, this will be about 3, this ratio of luminosities. So, this is actually what we see in simulations. So these ones, as I said, they come from nucleon conversion. And then the heavy neutrinos come from thermal emission and also a plus-minus annihilation in the neutron star. So here I show you the heavy neutrinos, and these are the electron neutrinos and antineutrinos as a function of radius at 0.2 seconds and then at 0.34 seconds. So this is the scenario of the extended accretion, which is the only one that we can actually simulate because they don't explode. We have some explosions that are triggered numerically that we use also to check what happens if you strip out, if you explode. And these are these black lines are the optical depth for proton electron scattering and diverse beta decay, but this I will discuss later. And this is in terms of the luminosities as a function of time. This is at 400 kilometers. So these are the heavy neutrinos, and these are like the electron neutrinos and antineutrinos, and this is the ratio, the thing that I showed you before, for several different simulations. So this changes the mass and the equation of state. So as you see, the cartoon that I've shown, maybe a little simplified, but basically it captures the physics. So it goes from 5 to 3, depending on the equation of state. In some cases it stops, and in some cases you just see a rise. Okay, any questions? Okay, so now this is the situation at the source. And now what are the detection channels at Earth? So the idea is, as you see, time scale and the flavor distribution, which is different. So the detection channels at Earth are inverse beta decay for the electron antineutrinos in a neutrino detector, and the rate is well, the number of targets, the flux, the cross section, and well, some Jacobian. There is a table, and you have to integrate over the minimum, so between the minimum and the maximum energy of the recoil of the positron. So these numbers will be important when you actually try to establish the significance of your discovery. And then there will be proton elastic scattering. The proton elastic scattering is basically flavor independent. Okay, there is some small dependence on flavor, but basically flavor independent. And here you get the sum over the fluxes. Now you have a lower limit of the proton recoil of the neutrino, which you don't see, and then you have the kinetic energy of the proton that you will measure. And again, these numbers, depending on how precisely they can reconstruct the scattering process, they will impact the significance. Now, so this is what is yes. So these are so T prime is this is just a technicality. So T prime is the real proton kinetic energy, and this is the minimum energy that you will see in the detector, and this is for two. These are curves for the efficiency of reconstruction for two different scenarios. 0.2, which is very conservative, and 0.04, which is actually somewhat optimistic, as a function of the average energy of the neutrinos. And well, yeah. So basically, if you have highly energetic neutrinos, in this scenario, you basically reconstruct all events. In this other scenario, you reconstruct 70% of events. And this A parameter describes variation in the energy spectrum of the neutrinos. So for reference, the average energy of neutrinos is probably around 15, but it can change. We are not sure about the spectrum like at this level of accuracy, so this is what I show you for reference. So then finally, another effect that of course you may ask are neutrino oscillations. Because you produce these things far away and then they oscillate. And oscillations will always average, because the supernova is just very, very far. And so the neutrino at Earth is just a linear combination of all the flavors. Just the survival probability is 0.68 minus this. So this is just a parameter which is basically very, very small, and it's the level crossing probability for a resonance. So the adiabatic limit is valid if you have a normal matter. If you have this site that you don't explode, we checked that the adiabatic lit oscillation is always valid. It may be violated in the explosion in the delayed neutrino mechanism at some point. It doesn't look like, but we don't know for sure. And anyway, this is a common and useful benchmark, just that you can calculate. And then there is this thing which are self-induced neutrino oscillations. So are they important? So these are two caveats for the oscillations. Now, the self-induced neutrino oscillations are actually oscillations that happen if your density of neutrino is very, very high. And so this is something that can happen near the core. But they shouldn't be important by estimate. So this is the proposed observable, which is basically the ratio of, so this is the Earth analog of the ratio of luminosities at the source that I showed 5 slides ago. This is the number of proton-electron scattering events versus the number of inverse beta decay events. Well, this is the inverse of that ratio, such that it's smaller than 1. And this is what we expect. And now I just explain what all these lines are. So the 3 colors refer to 3 different masses, and these lines refer to 3 different equation of state. We simulated some combination of masses and equation of state, just to show the variance in what we don't know, because we still don't really know the equation of state. And this is for the very conservative scenario of 0.2 MeV minimum recoil energy. As you see, I mean, so the delayed neutrino mechanism versus the site is, between the error bars you can see by eye that you can distinguish the 2 scenarios. And in particular, if you go to a better reconstruction of the recoil energy, like your significance is really perfect. So even just by these single statistics, where everything has been integrated, except for, well, this is the time dependence, you immediately see that there is that there is the possibility of discerning the mechanism.
So what is determining those error bars? Some of it is statistics, but evidently not all of it, right? Because you're...
So which one is which?
Huh?
Which one is delay? Which one is that?
So the delayed neutrino mechanism is the one that
the larger...
the larger one. Yeah, exactly. It's the larger one because it's the inverse of the ratio of the luminosities. Yes. So the error bars are determined by uncertainties in the statistics and then uncertainties in the energy spectrum and the oscillation parameters. So
that has to do with the discrimination between the electrons scattering?
no, well, these yes. These here I fix the proton electron scattering recoil energy, and so this is the difference between the two, as you see, right? And then, for instance, this is the oscillation parameter uncertainty. So there's a few things that contribute to the uncertainty. Also, the cross section for proton elastic scattering has some uncertainty due to the strange content of the proton. That's also uncertain. I mean, there's a bunch of things that we take into consideration. It's very interesting to check the oscillation uncertainty. Again, I show you for the very conservative and somewhat optimistic scenarios. So this is inverse hierarchy, and this is for normal hierarchy. This is the ratio as a function of the oscillation parameter of the survival probability. So in the case of normal hierarchy, we are able to distinguish things. In the case of inverted hierarchy, only really if you have the optimistic neutrino, the optimistic proton reconstruction. And of course, I mean, you can check that things are right because at point 33 you are not distinguishing anything. So, yeah. Okay, and in addition to have just the statistic, just one number, we also do a likelihood analysis exploiting the energy spectrum. And the energy spectrum that fits pretty well, it's called the pinched Fermi Dirac distribution. I don't know why pinched, but basically it's a Fermi Dirac with this parameter A added, the parameter that I was showing in the beginning, to go beyond the just number counts. And then we actually focus, we now can actually focus on the luminosity statistics, not just number counts. And as a function of the luminosity so here what we are trying to do is a likelihood analysis reconstructing the distribution of this parameter, which is the ratio luminosity, which is either 1 or from 3 to 5, 6, okay? So this, of course, is sight, and this is the delayed neutrino mechanism. Here, for sight, we use this particular simulation, and the two diagrams correspond to having either 3 kiloparsec, a supernova exploding at 3 kiloparsec, or a supernova exploding at 10 kiloparsec. Okay. Again, for the two scenario for the reconstructed parameters, and of course this just comes from neutrino flux, from observing so many neutrinos. So this is like either 3 kiloparsec or 10 kiloparsec with a detector which is 9 times bigger than this JUNO, which we take as a benchmark experiment. So even if you do a likelihood analysis, actually, especially if a supernova explodes close by, you really distinguish the two mechanisms by looking at the time distribution and the neutrino and the neutrino flavor ratio. So we got pretty yes.
And I think I'm not following. I thought that the previous thing was trying to basically count the anti-neutrino events versus generic ones.
Yes.
So what
So this is the same.
different?
This is basically the same thing, but before it was just a number count statistics. So you observe you get
So you're imagining there's one burst,
Yeah,
and then
so-
you
exactly.
right. You don't get very many supernovas, so you just take all the neutrinos,
exactly.
and then you
And
just
then,
try to classify them into these.
You
two
compute the rates,
Yeah.
integrating over everything that you can, and then this is just the number counts, and the error bars are just statistical plus physics uncertainty.
Yeah.
So this is just the numbers that you get per each bin in time. Okay.
Yeah, but then what is the? I think I understand that. It's the
Okay,
other one I
good.
don't
So the
understand.
other one is you take the data and you do a likelihood analysis for this parameter at the source by
I see.
checking, by
So
marginalizing.
vertical axis is a likelihood.
Yes.
Uh-huh.
By marginalizing over the other uncertainty. So this is the probability distribution of the parameter.
And you're somehow there's more kinematics in that? Is that why this is a better discriminant? Is there,
Yes, I guess,
you said timing? I mean, is there just there's more parameters that are going into this?
or, well, probably not. No, there are no more parameters, but so this allows you to quantify, let's say, the significance better, because you have the overlap of distributions here, right?
Okay.
The other one is a number count with, 2 sigma error bar or whatever.
Okay.
So they are equivalent, of course.
Yeah.
I mean, there are 2 ways to analyze the data.
Okay.
Okay, so this is a likelihood, and this in particular it's averaged in time, but you can also do the non-averaged in time analysis. And in this case, you can also reconstruct things in the energy direction, for instance, if you like.
So the likelihood analysis would be clearly what you would do if you had the real model. In other words, if you had a model that was accurate, right?
Yes.
But here you don't.
Yeah. Well.
So is this extra statistical power really meaningful?
What do you mean we don't? I mean, we have 2 classes of models.
Well, the details of the models are certainly probably not right? Like you said,
That is true.
Right.
That is true. But in fact, let me be clear. Here, what you do is the following. The only parameter that you need at the source is basically this ratio luminosity. So this is the uncertain parameter that you want to measure.
I see.
Okay?
So it's more
So-
like you're doing the detector physics more carefully.
Detector physics, oscillation physics, and we take into account the spectrum also with different uncertainties. So
Okay.
so these are all parameters that are kind of under control. I mean, it's basically normal physics Plus, of course, there is an uncertainty in the energy spectrum of neutrinos, but we know that they can be fit very well by this Fermi Dirac, pinched Fermi Dirac with a parameter which is of order 1. Yeah, and then this is the only real uncertain parameter that we want to measure.
But for these two now, do you input a particular number for this ratio, or there's a range of it? You have these two models,
Yes.
site and
Oh, you mean how this is done? Oh, yes. So so for this actually, yeah, we did a simulated analysis given a particular number.
For each
this.
model.
Yes. And of course you don't really know you say, oh, this is like 1.1 or 4.2 in the other mechanism. You don't know the numbers at this precision, but you definitely know that there is the time dependence of neutrino, and then in any case this number in the delayed neutrino mechanism must go back to 1, around 1, because you just produce neutrinos of all flavors. So this you know. And in this other case, you know that antineutrinos dominate by a factor of 3 at least. And so this is the difference that we know. And then we want to measure this parameter. And so if this parameter let's take this optimistic case, you get this parameter which is like 5. And then you see that the distribution is plus or minus 1. There is no way that this is delayed the neutrino mechanism. Yeah.
But what was your input number?
Sorry?
Was that accurate or close to 5?
Yes.
Something.
Yes. Yeah. We
Then show.
take it from the simulation. Yeah. For the delayed neutrino mechanism, we just take 1. Because these simulations don't explode. But for this, yes, we take the real number from the simulation. Yeah. So, any other questions? So this is just I'm being very honest here. So comments and caveats. The simulations which are not exploding describe site, and so the delayed neutrino mechanism, just what I just told you, is estimated by setting this equal at the source. Okay, and in particular, you can see that this is right the following way. There are simulations. There is this push thing, which is a numerical trick to trigger the explosion. Basically, what you do is you get the neutrino luminosity, and you increase the energy they transfer by 50% or 40%. And then you get an explosion in spherical symmetry. And this is the resulting ratio luminosity that you get, and this is 1. And these are 1D and 2D simulations. The 2D, these people, they say they explode. It's not entirely clear whether they are self-consistent with the neutrino mechanism. And in this case, the luminosity goes more about 1.5, whereas it goes up to 3.5 or 4 in the other neutrino mechanism. So this is the uncertainty that you get in the delayed neutrino mechanism. We just estimated this by for simplicity by setting this luminosity is equal, because we don't have simulations that explode. But you don't really get any big error in doing this.
For size here, you get you have about 3, but in the likelihood we construct about 5. Are they in the same simulation or?
No, these are pretty different simulation. I don't think. Well, this is. This I think it's due to the difference in equational state. There are some equational states for which these kind of flattens and others in which goes up. But usually this is the behavior that you see. I see
No,
your
yeah,
previous-
just if it's 3, then these 2.
Yeah, then the curves.
overlap a little
Yeah,
bit.
of course. No, I know. Yes, usually, I mean, the simulations that I did, I see this behavior, like, this number. This is about 5 when integrated over the post bounds, 4.5, and yeah, so same thing. So we are about here. Okay, so these are the conclusions. So as I said, I got into this because finally I found a real physics problem, like of, the ones that you can touch every now and then is good to have something that you can see and you can touch. So basically, is it
By our standards, neutrinos are such things.
Yes, yeah, of course. Yeah, I mean, I've been touched by neutrinos, but at least passed through. So, is it related to the core dynamics or different mechanism? And in particular, I showed you 2 more specific mechanisms that exemplify these 2 classes. So neutrinos, of course, are the ideal probe because they just, you see them, whereas photons, you only see the explosion. And we identify the best observable as the ratio of different flavors emitted. And we quantify the predictions and assess the impact of a lot of uncertainties. And so let's just hope a galactic supernova goes off once JUNO is built. So for at least 1 year, I hope it waits. Otherwise, we have to wait on average 100 years. Well, maybe less. Anyway, okay, I'm done. Thank you.
Try doing JUNO,
Yeah,
not
that's the same thing.
other.
Oh yeah, we
Why
can do
not
with
snow?
like
Why not snow? I thought there were things.
Yeah.
Separate
There are others. Yes, that's true. No, definitely. I'm
Snow is just,
joking.
Juno is just bigger. It's just
Yes,
basically
it just
better statistics
exactly.
and
That's the reason. But you can also try to do with. I'm not sure you can do with ice cube because JUNO in particular is very sensitive to these channels, proton elastic scattering versus inverse beta decay. Like it's built, so if you read their white paper, they are very sensitive to these different channels. Yeah. Yes.
So what's the world of mechanisms for supernovae? Are there other mechanisms that sort of populate that space and muddy the waters a bit, or?
Yeah, so about the first class, basically people discuss a lot the role of magnetic field and magnetic turbulence, and also convection. And so it's convection probably alone doesn't help, but it helps together with other things like magnetic field. Also, usually, so one interesting thing here is that you actually do. It seems that you do need an asymmetry for the explosions. And the reason is that most neutron stars that we observe, they have a high velocity, peculiar velocity. So there must have been some kick that they received during the explosion. So yeah. So this is for the inner core, people discuss this kind of scenarios. Mainly magnetic field is the alternative.
But how does that change? Do you have a sense of how the...
It's the same thing that you revive the shock. So basically the energetics doesn't change much.
Okay, so your signals will remain
Yes,
similar.
yes. So it's
pretty represent. So the
it
cases
is.
you looked at are kind of represent the
Yes,
state of the art.
yes.
Sort of, okay.
The other one for external, I mean, I was joking about dark matter, but actually, maybe not really, because so the only mechanism that I know that does not rely on the energetics of the inner core is this side. However, for instance, there have been, I think, a couple of papers by Rajendran and Graham, for which they use dark matter to trigger an explosion in type 1a supernovae. So white dwarfs that then they become white type 1a. Maybe something similar. You can imagine something similar here, but I'm not sure. Yeah. So yeah, that's the only thing I know. But basically, yes. So one is related to the gravitational binding energy of the inner core, and then basically we only rely upon the simple fact that the shock has to be revived, and then everything strips off. So this is the important thing that determines the neutrino luminosity. The other case, you still have the layers.
Do we know if this massive star died without explosion?
Well, starts with less than 8 solar masses. They
Yeah,
don't
I mean,
explode.
but the massive one.
Oh,
How they explode? If
you-
you say
Oh.
it's so difficult to get simulation to explode, do they?
well, we see them explode,
Yeah.
right?
But
So-
there are ones who don't explode.
Oh, you're
just die
saying that
by-
there are the ones
perhaps
who don't
without-
explode.
It's difficult for real ones too.
Huh?
It's difficult for real supernovae too.
Yeah, I don't know.
Or just because we don't see them, so we
Yeah, honestly, I don't know. It might be possible that you just form a black hole. If they don't explode, they would probably form a black hole because everything goes back. And then you just see an accretion disk after a while. Yeah. Yeah, no, this might be a possibility, honestly, right? Yeah.
In principle, we know how many massive stars there are. In principle, we know after the
Yes.
fraction of them explode, right?
We have some
By
uncertainty on the initial mass
frequency.
function, but yes, we can estimate, and this thing of like once per century comes from this. And they always assume that everyone explodes, yeah, when they do this estimate. But yeah, I mean, it's definitely a possibility, I would say. I mean, yeah, it's not obvious that they will explode, in fact. But, you know, some do, at least some do.
Yeah,
So-
it's awesome.
There are no more questions. Thank you again.